Everyone, welcome back to our Chapter 1 Reactions Kinetic. For this video, we are going to talk about Chapter 1.2 about collision theory. Here's the learning outcome which you can refer back to the notes given. So first of all, let's us look at the collision theory. So here is a requirement for a reactions to take place in which the particles must collide at a correct orientation. So this particle refers to any atoms, ion, molecule, or compound. But the requirement for reactions to take place, they must be in correct orientation. And the product will form only when effective collisions occur. So this effective collision is when you have this correct orientation. And all these colliding particles must possess a minimum energy which is equal to or greater than this EA. EA is the activation energy. So three of these are the requirement for reactions to take place: correct orientations, effective collisions, and a minimum energy is required. So this activation energy EA refers to a minimum energy required to initiate a reaction. Next, we have our transition state theory. In this theory, it explains the activation energy EA as the energy required by reactant molecule to form the activated complex at transition state. So the explanations over here, we're going to use a diagram to show you in more detail. So this activation energy is a temporary species formed by the reactant molecule as a result of effective collisions before they form the product. So activated complex is the species in the middle between your reactants and the product. And this theory is best explained using the energy profile diagram. So next, this is our energy profile diagram to explain the transition state theory. So we have our y-axis as the potential energy in kilojoule. The x-axis is the reaction progress. So initially we have our reactants. So in this case, here is the example of CH3Br and OH minus. So this species begins to break down. And slowly, when the reactions progress, it reaches until one point when some of the bond is in the middle of breaking up. Okay, and then it reaching this higher point, which we call as the transition state. Okay, transition state. And the species that is going to break the bond and forming the bond, this intermediate species, this temporary species, is what we call as the activated complex. Okay, and the reactions progress, it slowly turns into the product. Okay, so in this case, the bond breaking is completed and it forms a new bond. So over here, the energy profile diagram, you can see that we have a delta H which is negative. Okay, proceed from the reactants to the product. It releases the energy. Therefore, delta H equals to negative kilojoule. Whereas the differences in energy between the reactant and the activated complex is what we call as the activation energy. So this energy is needed to stretch and deform the bond in order to reach the transition state. Okay, so the reactor will need this minimum energy. So at least it can cross over this step and form the product. Alright, so for this energy level diagram is what we call as the exothermic reactions. So in our next slide, energy profile diagram, there is actually two types. One to refer to the exothermic reactions and another one will be endothermic reactions. So first we talk about exothermic reactions. You have a delta H, the enthalpy is negative in value, which refer to the enthalpy of reactant is higher than the product. Or more commonly known, the heat is released in this reaction. So this energy profile diagram, initially we have the reactants at higher energy, okay, and then it has to cross over this activation's energy to reach this activated complex, and finally to form the product. So over here you can see the difference in energy between the reactant and the activated complex is what we call as the activation energy. Okay, and then from the reactants towards the product going down, okay, energy is released. That is your enthalpy. Okay, the direction is going down, and then this enthalpy is negative in values. Take note that activation energy between reactant and product, we can also find the reverse activations energy. Alright, so reverse activations energy is the difference in energy or the minimum energy when we want to do a reverse reactions. So from the product towards the activated complex. Okay, so reverse activations energy we label as EA prime. Okay, it's between the product and the activated complex. Alright, next we have our endothermic reactions in which we have this enthalpy equals to positive value. So in these endothermic reactions, enthalpy of reactant is normally lower than the product, or more commonly known that the heat is being absorbed. So represent by these energy profile diagrams. As you can see over here, reactants you have a lower energy or lower enthalpy, and you need to have to cross over this minimum energy, the activation's energy, to reach this activated complex, and finally reaching your product. So the difference in energy between reactant and activated complex is your activation's energy. Okay, between reactant and activated complex is the activation's energy. Whereas from the reactants towards the product is our delta H. So energy is absorbed because it increases in energy. Okay, so this delta H single direction from reactants towards product, it will have a positive value because going outwards. So to figure out your reverse activation's energy, okay, going backward, so it is the difference between our product and the activated complex. You don't have to redraw the energy variable diagram. So straight away label it here between product and activated complex. So this is two types of energy profile diagram, exothermic, endothermic. So that's the end of our chapter 1.2, and there's no exercises on this subtopic. So I'll see you again in the next coming videos.